All right, and we are back, and we are going to look at some, basically, hopefully some statics review and some basics. So we're looking at shear diagrams and bending moment diagrams. So very similar process, coordinate system, free body diagram, equilibrium expression, solve for unknowns, but we're also going to cut the beam because we want to develop expressions for our shear moment and our bending moment to develop those diagrams. So again, for our cantilever beam, same process, figure out your reaction moments, forces, and now you start to cut the beam starting from an x equals 0 before the first load is applied. And we could then do the same types of expressions. And you can find that we now have an expression directly for our shear moment and our bending moment. So our shear moment is constant, equal to the load. The bending moment is a maximum at the location. We experience maximum bending when x is equal to 0. That should match with our intuition of the system, because basically our cantilever beam is fixed there, so that should make some intuitive sense, which is nice. You always want to have that idea there. The shear moment being constant is a little bit less intuitive, but that's a good double check to kind of see what we're doing. You can also see, again, this should technically, again, experience negative bending. You see that our expression there, but that will come out again with the negative basically P that's applied. So again, you'll eventually get your kind of correct solution even if you keep it in this form. So we can do the same thing for a 4-point bending experiment. This is a very, very common type of bending. We will probably do this in our class. So again, coordinate system, free body diagram, equilibrium expressions, solve for our unknowns, reaction moments, reaction forces, and then we need to cut before the first load is applied, after the first load is applied, and then we're going to get two expressions because, again, this is a symmetric type problem. So we see that the bending moment, or actually our shear moment, is actually 0 there. You can also look for a distributed load. Again, it's just the same process. You've done this before. You've developed these expressions for other expressions and other equations. But the key thing that we're going to see here with this distributed load type problem is we're going to develop a very general equation. Specifically, that we can relate our shear moment to our bending moment. And we can actually see that there. Here you could actually look at, you could relate the shear moment to your applied load Q. But we can develop a relationship between our shear moment and our bending moment diagrams here. So again, these are things that you've seen before. This is going to be very important once we get into essentially beam deflection and how we're going to solve quite a few of those problems as well. But you can see here, we eventually, again, if you work through all this math, we'll find a much quicker way of doing this, but you'll have your expression for your shear moment, you have your expression for your bending moment, for your distributed load scenario. So next time, we're going to get into stresses in beams. See you then.